Okay, so next up is Liam. Okay, so Liam's going to tell us about the work of Counterfactual, which you should all probably be aware of already. So this is awesome. So I'll let you just jump right in.
All right, cool. Can this work? All right, cool. Nice. All right, yeah, so my name is Liam. I'm the co-founder, one of the co-founders of L4. I've been involved in all kinds of things. I had the interesting coincidence of being in the same class of Vitalik several years ago, where he kind of first started talking about Ethereum, and that's how I first learned about all this stuff. I've just been fascinated ever since, but never really dove deep until fairly recently, where basically I had an idea that basically this technology is going to kind of change what we kind of consider to be the web today, and so we try to work towards building what we're calling Web 3. And so the vision of L4 essentially is to build Web 3, and we do three main things. One is supporting the research and engineering of bleeding-edge cryptoeconomic systems. So we work a lot with state channels and plasma research, things like force-move games. And we also work on things like ETH Global, which are the largest developer events in the industry for hackathons in that sense, and a fund called the Stable Fund. One of the main things that we do in terms of our state channel research is we're trying to pioneer this framework called Counterfactual, which we want to kind of turn into an open source framework that takes a lot of the best learnings from everyone here, essentially, and turns into something that's practically useful for the thousands of developers that we're attracting at our events. So, what is Counterfactual? Fundamentally, the project is meant to be a bridge between the best state channels research applications of the technology, kind of as I just mentioned. So, we do two things. One is research. We recently released a paper called Generalized State Channels, which is kind of the summation of a lot of the thinking that Jeff Coleman and us at L4 have been doing over the past little while, and much of which is from Jeff Coleman and when he initially kind of talked about state channels in 2015. And that's online. You can read about it. And we're also focusing on engineering, so that the actual practical framework where we are contributing very heavily at all layers of the stack, implementing contracts that actually make the stuff work, the channel clients, thinking about that, a web framework, which Eric, one of the core team members of Counterfactual, will talk about, and then actually trying to build real applications using it. So what am I talking about? I'm going to try and cover some of the key insights in our research, and kind of leading up to the next talk, which Eric will give on how we've actually started to build this. So these are the main things, an overview, as we've done many times already in this conference. I'll do it really quickly. Code-based addressing, which is our technique for allowing off-chain code execution, and kind of building frameworks around it. Meta channels, which is our technique for routing effectively. Then a few advantages of the approach, and an interesting kind of thing I'll mention about unavailability griefing. So, first part. What does generalized actually mean in generalized state channels? We've been talking about this for a while, but what is the actual fundamental difference between that and like a regular state channel? I think it's been talked about a few times here, but there's kind of like these differences in what you can do with a state channel. There's like Christina mentioned, there's multi-contract in a state channel, or there's a single contract in the state channel, or just a payment channel. One of the main ones that we've been talking about for a while is an app-specific channel. So for example, you create a transaction to put a contract on chain, you iterate through some state updates, and then that is then taken back to the chain, and then that is ultimately your single app channel. We think basically a generalized channel is one where you can do that whole sequence of operations without any on-chain transactions whatsoever. So a state channel is not quite a single application with state transitions. It's actually a container of multiple applications that can all be running at the same time. And so that's been like the key thing that we've been driving for. And again, that means you can install applications and do all these things with no on-chain transactions. So just to cement that, here's our kind of classic example that I'll show just how we can do payments or installation of new applications and what that kind of actually practically looks like. So here's a setup. There's Kasparov and Karpov, and they're playing chess as they usually do. And we have a single on-chain contract. I'll talk more about this contract in a bit. But it has 20 ETH inside of it and 10 DAI, which if you're not familiar with DAI, it's the MakerDAO stablecoin. And effectively what they're doing is they have some balance, as you normally do in a state channel, between Kasparov and Karpov. They have 5 DAI each, and they've also already set up a chess game where the winner gets 20. So this is a typical thing you might see in an app-specific channel. Well, the first thing is, how do you start doing other interesting stuff like a payment that's unrelated to the game? There might be a situation where Kasparov happens to run a coffee shop and he wants to sell coffee to Karpov. So you might say, hey, do you want a cup of coffee? I'll sell it to you for 3 DAI. Karpov will agree. They then sign a state update with a slightly updated sequence number. It's a bit small, but sequence 8 was the initial sequence number of their free balance. Now you update the sequence 9. And once that's been signed, you can comfortably send over the coffee, and that essentially trumps the past one and becomes your new state. So that's a typical process by which you might add a payment. And then what if you wanted to, say, add another game called Go? It's an interesting game that they're not as familiar with, but they'll play it. What you do is you set up a state, you set up the bet, first of all. What's the purpose of the game? The goal here is you want to bet 1 DAI each. So the idea here is we want to take some money that they've already put into their free balance and assign it as the result of a game. So first of all, set up the game. Both parties sign a commitment that says that there exists a game. And then what you do is you update the free balance atomically such that the money that they had in there goes into the game such that the rules of the game play out who gets that money. Effectively, they then play the game, and effectively now, after having been done, the winner getting 2 DAI, you just simply look who the winner might be, and in this case, it looks like it's going to be Karpov. Kasparov can resign, or you can go on-chain in the similar dispute mechanism systems that we've talked about, and you update the state. So this is a typical situation where 2 people want to do something with another counterparty that's not the same game, it's different logic, different bets, different conditions, and it all kind of goes like that. I think these slides have the hidden slides. So I'm going to have to do this for a couple times. 1 sec. OK. So during this entire example, there have been no on-chain transactions or fees at all, the whole time, which is the main thing that we want to achieve by having multiple applications in the state channel. So why is it useful? This is where it kind of comes into the bet that we're making is we think that fundamentally decentralized applications are going to be the kind of thing that are just a default experience in Web3. Users are going to expect these things to be fast, cheap, easy, regular. It's the same as you would any application. And they're not going to want to have to deal with a blockchain just to use a new application or to update another one or to move money between them. Web3 should not involve constantly having to get your wallet out. And so we think this is actually going to be one of the most fundamental innovations that's going to take this technology and make it mainstream. So that being said is basically state channels are the foundational technology for usable distributed applications. So what I just showed you, again, is that you can install new applications instantly. Users don't have to wait for the next block, start using a new app, and there's no fees to install new applications. So how? The main innovation that we've been kind of trying to, or the 2 main innovations we've been trying to jump is 1, you don't need much on the actual blockchain. Really, all you need is something that can sign, that can accept signatures from the parties in the state channel and execute a function call. That's about it, which you might be familiar with. It's a multi-signature wallet. It's the only thing that you really need. And so as long as it can hold assets, ETH or ERC20 or ERC721 or whatever, you don't really need anything else other than that. All of the rest of it can be on-chain. And the second thing is you need a way to reference that stuff that's off the chain. And this is basically the technique of code-based addressing. So I'll kind of talk about that. Effectively, that is basically the way where you might have a contract off-chain that you might have a contract period that you want to be able to reference as the logic that you'll use to kind of figure out who won some game. And you don't want to have to put all of these contracts on chain. Right? We're going to have like thousands of tic-tac-toe games on chain all the time. It's much better if we can reference these objects off chain because they're going to want to be upgradable and you're going to want to change them and they're going to be a bit more complicated. So how do we do that? Effectively, since we don't have fixed addresses, we need a kind of a solution for that. Well, we need deterministically generated addresses. Thankfully, there is actually an EIP for this, which is Skinny Crate 2, which is a ridiculous name, but effectively what it does is it allows the address of a contract to be computed via the SHA of the message sender, a user-generated salt, and the init code, which if you're not familiar with that, it's the contract bytecode and the constructor arguments basically appended together, which means you can compute deterministically the address of any contract, which means the tic-tac-toe game between like me and Jez that's being played for some amount of money there already exists an address for that. We don't need to go to chain and put it on chain and then know the logic's there and then reference it. It already exists. We just need to compute this hash. So how is that useful? I'll show an example where you want to just send money to something that doesn't exist yet. Okay, so same idea. Blockchain has a multisig on it. You want to have some counterfactual object. It doesn't matter what it is for the situation. You just want to send some money to it. It's, first of all, you get the code. So whatever it might be, it's some contract. You do the hashing to generate your deterministic address. And then you sign a regular Ethereum transaction, just this normal transaction, nothing special about it, multisig transaction, to that address. And effectively then, you put the code on chain, and then actually you don't actually have to put it on chain. You can still actually send money to an EOA. And submit this to the network, and the money will get sent. Which means, in this step here, when we generated this transaction, we kind of assumed ahead of time how it would work, despite the fact the chain doesn't actually have this contract on it, which is super useful. Another example is more practically speaking, what about a payment channel? Okay, so this is a payment channel that has to be in a finalized state before a payment is actually executed. What you would do is you generate the contract, which is your regular state channel contract. You have a timeout, and you have to have the balances of each person, and there's a notion of if it's finalized or not. Generate that code, same idea. Generate a signed transaction to it, but in this case, there's a condition. What you want to do is check if this contract is finalized, which is a function call on that contract, which you can see right here. So what you do is you sign a commitment to a conditional payment, kind of like what Patrick was saying earlier. A lot of these kind of boil down to conditional transfers. That says send the money based on what the variables A bal, B bal are in that contract. So you put the contract on chain, and now this thing actually will execute if you go on chain. So in the case of a dispute, you wait for this thing to be finalized. It's a finalized payment channel. You submitted the latest state. You have 3 and 7 for A and B. So you submit that conditional payment signed transaction to the multisig on chain, and the money gets sent out. So this is useful for things like payment channels and far more. So what are these things? What is this thing that we're doing over here, and what is this contract here? We're trying to introduce a bit of a terminology here that we're calling counterfactual instantiation, which people are starting to talk about in the industry. And effectively what this is, it's the method by which you can actually agree to any arbitrary condition off-chain. So I guess the main way that we're kind of looking at this is that means that off-chain code is law. Right. Anyway, no, but more operationally, specifically, this is the act of signing commitments to that multi-signature wallet that make a function call to a conditional payment operator that define the logic of counterfactual objects, those contracts that aren't on chain yet. That is actually instantiating a contract, bounding yourself and your counterparty, or counterparties if it's end party, to a particular object that doesn't exist yet. So, quick note. This doesn't exist yet, but there's an easy way to get around that, which is this thing called a registry, which is a contract that is effectively a mapping from those deterministic addresses that I mentioned to the actual on-chain address. So when you're making your signed commitment to an object that doesn't exist yet, you're actually making the signed commitment to this kind of proxy contract. For example, if you want to deploy a contract, what you're doing, you'll be signing a commitment to the deploy function with the bytecode of the contract and in any constructor arguments. That deploy function actually deploys the contract on chain, and in one foul swoop, effectively, also adds it into this dictionary, which means it's a kind of a deterministic way of actually deploying these contracts. So what kind of stuff can we do with this? One philosophy that we've had is we've been trying to think of a way of taking that technique and actually applying typical best practices for designing software. And in one particular is this notion of object-oriented design. And so we think that if you actually build all this infrastructure, you now have basically a way to do arbitrary off-chain computation. You can design any application you want, right? There's very little restriction. It just contracts to reference each other, which is the same as what you can do in Ethereum anyway. And so what we're trying to figure out is applying these common techniques to the design of those types of systems. So there's things like compartmentalizing functionality into multiple, into similar kind of components, reusability of code, and things like that. So one common example that we show is dependencies. You want to have that typically in your objects. So basically what you can do is you can just write your code to include in it a reference to some other contract that uses, in this case, just a regular address, assuming crate2 exists, but if registry was there, you'd use the registry.resolve function to require that another object is finalized before this object is finalized. So this is like conditional hierarchical finalization, effectively. So then you have that other object. It's just, again, it's another object. It's a typical state channel object. You sign commitments, and there's a timeout, and eventually it's finalized. Once it's finalized, you kind of have a situation that looks like this. your first contract that was on the right and your second contract that is depending on, effectively these two things are joined. And so they must both be finalized in order for the payment channel to be considered complete in this example. And that means you can do all interesting stuff. One example is you can minimize the cost for deletion, or effectively making state invalid. For example, this thing depends on that. So it doesn't matter what this is if this dependency is broken. So if you increment it to 4 by assigning a commitment to this object and not that object, you effectively come up with a very simple, small amount of state update to handle disputes, for example, where this payment channel goes on-chain. Interestingly, this is also useful for things like atomic swaps. What if you have a payment channel, or not even atomic swaps, but just atomic state transitions between objects? What if you have a payment channel, and what you want to do is you want to initiate your game of poker, or like I was showing in the early example with Kasparov and Karpov installing Go. What you do is you kind of set up another version of the world. You start with this version of the state channel, which is valid because the latest signed update is 3. You set up a new version of the world where if the number were 4, then the payment channel would have decremented its balances, 1 each, and there would be a poker where the winner gets 2 each. So you kind of set up what you want the world to look like in a way that can happen asynchronously. It doesn't matter the order of the signed commitments, as long as they all depend on 4. And then once everyone has both signed copies of both of these things, you can increment the nonce to be 4, and you've atomically switched to an entire new setup for your the state that you have off-chain. So that's a core technique that we use for something that we call meta channels. And you're probably familiar with meta channels. It's the same idea, effectively, in spirit, of being able to route payments and route state transitions through other people that are willing to provide capital or arbitrary state, depending on what the situation is, to enable you to do that without an on-chain state channel actually existing. So here's an example. In this case, we have 2 state channels. One that's the Alice Ingrid state channel on the left, and one that's the Ingrid Bob state channel on the right. And you may have noticed I've kind of separated this in a way that is showing that because we're not doing anything particularly we haven't added unnecessary restrictions to the style of which these counterfactual objects exist. They're just some contract, some code that you can reference. You can actually have an object or an item that is referenced by both state channels. And this is actually very useful for all kinds of things. In this situation, it's setting up a meta channel, and I'll show how that kind of works. What you do, and again, just to quickly make sure they're on the same page, starting with this Alice Ingrid Alice Ingrid channel where they have their own payment channel, and Bob and Ingrid have their own payment channel. You're kind of instantiating these in-between objects that point to another counterfactual object. And again, this is just a regular object where Alice has some amount, Bob has some amount. It's just state. Same thing here, Alice, Ingrid, Bob over here. And what you're doing is you set up these interesting proxy objects. So what's a proxy object? Effectively, what you're doing is you're signing a commitment that will ensure the integrity of the meta channel, such that no matter what, Ingrid will get paid out. And in this case, it's a similar idea to what Christina was talking about, where the game must be played out in a way where there's one winner, one loser, and basically Ingrid gets paid out for both cases. In this case, you're basically setting up a contract that points to this other contract that's agreed upon by both, saying whatever the state of Alice's balance is at the end goes to Alice, and whatever the state of Bob's balance is goes to Ingrid, and the converse on the other side. So this ensures that Ingrid is going to receive all of her money, and it also allows them to have just this single object that they reference. And nicely, Alice and Bob can just message each other like they would in any regular payment channel situation. And the cool thing is these things can actually be composed, where you just set up proxy payment channels that point to the same object for any route, say for example an Alice to Bob route where there's multiple hops going on. And effectively, all you need to do is just have the single object, allow Alice and Bob to update that, and you just ensure that you set up the proxy payment contracts such that each party will get paid out accordingly, and there's no imbalance along the way. Actually, this is again a slide that I didn't add. So one thing that's interesting to note is that this is, because again, it's general and it's flexible in what you can do with it, it allows us to set up constructions that achieve similar efficiencies as, say, sprites on Bitcoin, but in our circumstance here, where you can essentially have order 1 lockup time because all the contracts are simply pointing to the exact same independent object. So this is similar again to what Patrick was talking about earlier with the sprites construction, where there's just a single thing upon which all the conditional payments refer to, and its finalization triggers across all of them. And this is very nice property. And just for reference, this is a similar model to like the circuit-based model, and in the prune case, the rent-a-path, what we're calling the rent-a-path model, where you don't actually just like for each payment kind of have a set up the chain of payments and then execute it. You actually set up a path, and along the way, the capital is lent during the time that that path is open. So it's a fundamentally kind of different construct. And these are the kind of things that like Seller Network and others are kind of taking advantage of. So one thing I wanted to touch on a little bit, that's just an interesting thing to note, is there does exist a griefing vector in other types of constructions that if you have this kind of flexible model, you can avoid. So specifically, the case where Alice, Ingrid, Bob, they're doing a meta channel. Ingrid can be griefed effectively if Alice and Bob choose to just collude to force Ingrid to go on chain in scenarios where Ingrid is trying to be an intermediary. So this is kind of like what we were looking at with Prune earlier, where Ingrid is kind of is responsible for dealing with the resolution of the state that Alice and Bob are doing in their state channel. If you simply restrict the output to being like a payment effectively, then you can not have to require Ingrid to deal with that, and in a sense you can basically avoid having to have a resolution process that Ingrid is involved in. Instead, it's up to Alice and Bob to finalize the state on their own, and Ingrid is simply locking up her money for some condition. Summarizing that effectively, this is kind of something that you can see if you force Ingrid to be in that position. However, if you, in a meta-channel situation, remove Ingrid's involvement such that she only needs to know that Alice and Bob need to finalize their state by some time, that allows you to not to remove that griefing vector. Another thing to note is that onion routing basically comes for free in the approach. It's simply a matter of constructing those proxy payment channels in a slightly different manner. And it looks a bit more like this, where instead of each proxy payment channel in the old design kind of pointing to a single contract, they actually kind of have a bit of a nested structure, such that each party, while off-chain, only can see what the proxy payment is of their partner. And so they don't, for example, in the Ingrid Alice channel, they don't actually care what's going on over here. All they know is that interest is going to pay out, and that's fine enough for them. So handful of other advantages to the approach that I wanted to quickly touch on that are interesting, just things that are unique to the approach right now that we think are things that are worth exploring in other approaches. We'll just go through them. One is the bootstrapping effect of having multi-signature wallets already on chain and the privacy benefit. Since these are all multi-signature wallets, there already are a bunch of multi-signature wallets on chain. So effectively, we already have a bunch of state channels on chain. And secondly, they're no different to a state channel. A state channel is a multi-sig is a state channel. There's fundamentally no difference in the on-chain component in our design. This is also a privacy benefit, of course, because if I'm in a state channel with someone, it's indistinguishable from just being a regular multi-sig on the chain that me and that person happen to have together. Again, upgradability is super useful. This is one thing that's happening a lot in the industry right now. For example, OpenZeppelin just released Zeppelin OS, which is actually having on-chain upgradability. If all of your applications are off-chain, thankfully you don't need to use that, and you can actually, if you find a bug in your contract, assuming it's beneficial for both parties to just move forward and fix the bug, they just sign updates. It's effectively changing the address to the new generated address based on the new bytecode that fixes the bug, and everyone moves forward and the bug is effectively fixed. Again, no on-chain transactions for upgradability. Super useful. More so than that, another advantage is that you can generalize your state deposits by default. You don't need to add new functionality to your on-chain contract to deal with new assets. So one common thing that we're seeing with a lot of approaches right now is the on-chain contract has function calls for ETH or function calls to transfer ERC20 or ERC721. That is not necessary to be on-chain as well. In this design, effectively, as long as there is a system for which an account can have control over an asset, let's say, for example, a chess leaderboard, the output of a state channel, the finalization, what happens in the finalization scenario of a state channel is just a function call from the multisig, which effectively is all you need to do things like transferring your ERC20 token, or updating a leaderboard, or transferring CryptoKitty, or anything like that. And this has become the new way that a lot of applications are built in Ethereum as well. More so, you can basically easily compress code because the multi-signature wallet just makes function calls to things. The more we can generalize the code that we're referencing, like common turn-based game components, common like force move game components on-chain, things like that, we no longer need to continually redeploy new contracts for common functionality that state channels will reuse. And partial withdrawal is something we always talk about. We can actually just do a simple partial withdrawal just by making a regular multi-signature wallet transaction. I was going to go into unavailability griefing, but I do have 5 minutes. Is that 5 minutes for questions as well, or no? Oh, okay. So I'll just quickly go through unavailability griefing. So this is something that's important to consider, because this is essentially the scenario where Alice and Bob in our state channel, Alice wants to update to make the next move in the tic-tac-toe game, whatever it might be, and Bob doesn't respond. It's a typical scenario where you see, there might be a chance that if I just stay unavailable, I can find a way to either grief my opponent, or maybe there's a chance that I can get away if they're not on the line to handle a dispute. This is basically the common speaker listener fault equivalence problem that we have to all kind of find a way to solve. We're trying to introduce a language or way of thinking about how to solve these problems, and we have kind of 2 ways to approach it. So the first is I want to explore this game theoretically. If you look at this, effectively what's going on is, if both parties just remain available and they're honest and they respond to each other's messages, that's the standard case. But if someone's unresponsive, they can just force you to go to chain. And that's just a net loss for the person that has to go to chain. They have to pay fees, and this is just annoying. It's a griefing attack, effectively, and right now is an unbounded griefing factor. So what's the solution to that? Well, okay, we can try to do a bit better. What if we could do like a 1-to-1 griefing factor? How would we do that? Well, we need to split the fees. And so this is what that would look like. If you can figure out a way to split the fees to going on chain, then now the incentives have changed, such that going to chain is actually something that both parties pre-commit to ahead of time in their state channel. This is a common technique you want to apply for all of your state channel applications. The other party has to pay too. So griefing is no longer something you can just do just to make them lose money. You have to pay to grief. But this is still not great, because if you're rich and I'm not, you can just spend all your money to make my life miserable, and for me it sucks. For you, it's not a big deal. So the next solution after that is this notion of bounded economic risk, which intuitively is we pre-commit that, okay, if we're going to do this thing where in the future where one of person submits the chain and then you stay unresponsive again and have to submit the chain again, and this keeps happening over and over and over again, and you just make me lose my money, then we can at least cap the amount of money that we're going to lose. So an example for that is effectively, let's say a tic-tac-toe game. A tic-tac-toe is, if it's simple, have a chess game where you can agree ahead of time that if there is a scenario where we do that dance like 10, 15 times, you go to chain, and then you're unresponsive again, and I have to go to chain again, and you just keep continually griefing me, then after, say, like 5, 10 moves, we just agree to end the game there. It's not optimal for chess, you probably don't want 10, but it's an approach that you can use, and it's a metric that you can use for figuring out what is like a number that we can kind of agree is the most likely number to ensure that if you start griefing me, it's not going to just impose long-term and boundless costs. Again, kind of like I mentioned, there's trade-offs. You're changing the rules of the game, which is not something you want to be doing generally if you're going to be designing a framework for arbitrary games, but this is a technique you can apply if you're trying to find a way to avoid those griefing vectors. And again, some games are so complex that you can't even figure out what a K is such that it would make sense. Of course, you can design more complicated systems than just a linear approach, but this is something worth researching. So yeah, that's the most of everything I wanted to talk about.
Awesome.
Yeah.
Fantastic talk. Is there... Yep, there you go.
Hey, Liam. One thing I've noticed from quite a few of the talks is that the happy case and the unhappy case, people assume that the happy case is going to be almost all the time, whereas certainly in our experience, as being one of the few state channels that are live, is that it's quite normal behavior for people to not close their channel and to just in our case, quit the game, not actually quit the game, just walk away, like go do something else, go have dinner or whatever, or not play a game for another day or two. So actually the dispute case is actually much more often than people think. And this presents a problem when disputing is expensive. And I know you're trying to share the cost by having people upfront pay, but keeping the cost of disputes down is actually very important because it's going to happen a lot more than you think.
Yeah, I would agree. I think this is an area of optimization in Solidity code, I think. In our model right now, like what I showed, basically you can kind of have like a sequence of levels of complexity of your conditional transfer. So for example, you can have a completely arbitrary conditional transfer function which allows for multiple conditions to have to be true. You grab the state, you then run multiple interpreter functions on it, and that can be extremely costly. Or you can have much simpler games where the actual dispute handling can be like an extremely small amount of gas. So that's like one optimization that we make.
We need to get the gas cost down though, somehow.
Yes.
I mean, I don't just mean, I mean in general.
Yeah, 100% agree.
Any other questions? Yep, left terrace.
Hey Liam, very nice talk. Just have a small question. Didn't understand something. You were talking about upgradability, and you said that there are no on-chain transactions for upgradability.
Upgradability, there's no what, sorry?
No on-chain transaction.
Yeah, that's right, yeah.
That is assuming that we all agree to upgrade, right?
Assuming the parties in the state, yeah, that's what I was saying. So let's say, for example, that, I don't know, let's say we're using the force move game framework, and someone wrote a rock, paper, scissors game that is just completely broken, and we're midway through the game, and someone discovers this bug. There's kind of two scenarios. If the bug is advantageous for one of the parties, then it'll probably be exploited. But if the bug is disadvantageous to both parties, that in a way that if there was a dispute, it would just be completely exploitable on chain, both parties can just agree to upgrade. And again, this is true for all of the code that you use within your state channel. The point is, if you require unanimous consent of the users within your state channel, which will tend to be the case, they'll want to upgrade, then you just simply upgrade it off chain, and it's a matter of a framework having to just propose the update to the user, not necessarily needing to go on chain to reference a different object or anything like that.
Yeah. Okay, thanks.
Yeah.
And is there any other questions? No more questions? Okay, thank you very much for that talk. That was awesome.